All right, so let's prove a theorem about how limits of functions behave under the common operations of addition, multiplication, and division. So this is a very quick, it's an extremely quick proof, and it's a pretty simple statement here. So this is probably going to be a fairly short video. So I'm just going to go ahead and state the theorem here. So this is 20.4 theorem. So let f1 and f2 be functions for which L1, which is the limit as x approaches a along S of f1 of x and L2 is the limit as x approaches a along S of f2 of x. Both exist and are finite, yes. So you can actually adapt this theorem to include cases where L1 or L2 might be infinite, but you have to do it really carefully because, well, you'll see why. But yeah, you want to avoid these like indeterminate expressions basically. So the limit as x approaches a along S of f1 plus f2 of x is the sum of the limits, right? The limit as x approaches a along S of f1, f2 of x is the product, and this is, so if f2 of x is not equal to 0 for x and S, then the limit, and if and L2 is not equal to 0, then the limit of f1 over f2 of x, and this is as x approaches a along S, equals L1 over L2. Okay, and notice that a may be plus or minus infinity. Okay, so a is actually allowed to be infinite in these statements, but L1 and L2 have to be finite. And that's just because, like, you know, imagine if L1 was positive infinity and L2 was negative infinity, then this could be like anything. I mean, this could be positive infinity, it could be negative infinity, it could be a finite number. That's what we call an indeterminate form. And the same thing goes here, like if L1 was infinity and L2 was 0, we have no idea what this limit might be. So there are some cases where you can say definitely, like, okay, if L1 is finite and L2 is infinity, then this should definitely be infinity, for example. Or like if, you know, if L1 is non-zero and positive and L2 is infinity, then this should be infinity, or something like that, right? So you can make all these different sort of little, you know, modifications to allow for certain cases where one of them might be infinite, but you have to be really careful about that. So that's those are kind of left as exercises, and I think yeah, it'd probably be good for you to, even if that's not on the homework, which I don't remember if I put it on there, but even if it isn't, it would definitely be good for you to like think about, you know, what are the valid ways of like letting one of these be infinity. Okay, so let's just look at the proof. It's very, very quick because it really just relies on you know, so it just relies on the section 9 theorems basically. So let xn be a sequence in S converging to A, right? Then, or sorry, not converging to A, with limit A. Right, because remember, x, like A might be a plus or minus infinity, so we wouldn't want to say it's converging to A in that case. Okay, so then, right, so then by assumption, we have limit of f of xn, f1 of xn equals L1, and the limit of f2 of xn equals L2, right? Okay, so then by theorems 9.3, 9.4, we have the limit as n approaches infinity of f1 plus f2 of xn equals the limit as n approaches infinity of f1 of xn plus f2 of xn, which equals the sum of the limits. I'm just going to jump. Yeah, yeah, whatever. Yeah, so you can separate these, you know, of course, that's just what 9.3 tells us. And similarly, the limit as n approaches infinity of f1, f2 of x equals L1, L2. Okay. Also, if L2 is not equal to 0 and f2 is, sorry, f2 of x is not equal to 0 for, sorry, this should be a 2. For x in S, then f2 of xn is not equal to 0 for all n. So 9.6 shows that the limit of f1 over f2 xn is L1 over L2. So that's it, right? We took an arbitrary sequence approaching, or yeah, an arbitrary sequence whose limit was a, and then we showed that, you know, the corresponding limits of the values of, you know, f1 plus f2, f1 times f2, f1 over f2 with some slightly modified assumptions gave us the limits that we expected. So, you know, that there you have it. You know, our section 9 theorems come through once again, much like they did when we were doing the analogous theorems for like continuity of functions, right? It just boiled down to the fact that we've shown these sequences, like these theorems for sequences already. So it's kind of like we already proved that. Basically, you should think about it this way. We already proved that addition, multiplication, and division are essentially continuous operations, okay? Like the sum of two things varies continuously as you modify the summands continuously, or the product of two things varies continuously as you adjust the factors continuously, right? Or same with the quotient of two things. So that's basically the idea that those section 9 theorems encapsulate. So it's like we shouldn't have to redo that every time we come up with a new like concept of a limit, because we already know that addition, multiplication, and division are basically continuous operations. So they should preserve all limiting processes. So anyway, or they should respect, you know, all limiting processes. So that's it for this video. In the next one, we'll go ahead and, oh yeah, we'll look at the composition of functions. Yeah, which is a little bit more dicey. Okay, see you then.